Chapter 6, Estimation Procedures, Determining Transportation Budgets and Policies, a video submitted by Agnes, Lynn, Sana, and Peter for Political Science 3N06 tutorial. The learning objectives of this video are 5 key points. Number 1 is to expand on the knowledge of quantitative methods for political science research. 2, introduce inferential statistics. Chapter 5 introduces inferential statistics, and Chapter 6 expands on some of these concepts. So far, from Chapters 1 to 4 in the Healey and Prus textbooks, we've primarily been focused on descriptive statistics. Number 3, provide an example of a research question answered through the use of confidence intervals. Number 4, understand how to calculate confidence intervals by hand. And number 5, learn how to use SPSS to calculate confidence intervals. In 2006, the federal government spent over $3 billion on infrastructure projects under the category of transportation and communication from an estimated budget of $220 billion. Since then, the federal government has devised an economic action plan that aims to continue infrastructure projects and create jobs. These initiatives are primarily focused on road building and maintenance as opposed to the provincial focus of public transportation. Ontario, for example, is attempting to push a large-scale public transportation project called Metrolinx that expands current transit systems, incentivizing less car use. The federal government's plans ultimately favor the use of cars and other single-passenger vehicles. In order to justify these policy proposals, the federal government must show that these initiatives are pragmatic solutions to transportation issues across Canada. Our question for this research is, what proportion of Canadians use cars and/or single-passenger vehicles? One way to answer this question is to look into how many Canadians rely on driving to get to work. Our sample dataset was taken from the 2009 census. You can find the dataset on the Nelson website for the second edition of the Healey and Prus textbook using the highlighted link provided. Our sample consists of randomly selected individuals in Canada in 2009. Our population is the entire population of Canada in 2009. Using inferential statistics, we can link the sample and population datasets. While descriptive statistics are useful for many things, inferential statistics are more appropriate for these purposes. The following is a representation of our dataset taken from SPSS. There are detailed instructions later in this video on how to make this output on SPSS. We are focusing on the information in the second row, highlighted by the red box. This information is on car, truck, and van as driver use to work by our sample group in 2009. It shows us that the frequency of use is 675 from a total of 1,500. This makes up approximately 45% of the sample population.
To begin, you must look at your sample and determine which formula will be best for you to calculate your confidence interval. Since we are looking at a sample from the 2009 consensus titled Mode for Mode of Transportation, the formula for proportions will be used. Here is the corresponding formula. CI is equal to PS plus or minus Z times the square root of PU bracket 1 minus PU bracket over N, where PS is the proportion sample, Z is the corresponding Z score, PU is undetermined, and N is the number of cases. The first step is to calculate PS. You must look at all the categories within the heading, which for us is cars, trucks, and vans, add them up to determine your frequency, which was 675. The total number of cases within this category was 1,500. You must convert this into a proportion so it could be used in the formula. The formula for a proportion is P is equal to F over N, which is 675 as the frequency over 1,500 for the number of cases. This equaled 0.45 and became our PS variable. The next step is to set your confidence interval. Typically this is set to at 95%, therefore giving us a 5% probability of error, also known as alpha. This too must be converted into proportion using the previous formula, P is equal to F over N, which is 5 over 100, and the answer becomes 0.05, becoming our alpha variable. The third step is to determine your Z score. If alpha is set to at 0.05, then the corresponding Z score will be plus or minus 1.96. The fourth step is to determine your PU variable. Because PU is unknown, the variable will be set at 0.5 PU. This allows for the maximum value this expression can attain. Now that you have all your variables, you can plug it into the formula, where PS is equal to 0.45, Z is 1.96, PU is 0.5, and N is 1500. And it will look like this. First, you have to deal with what's under the square root sign, which becomes 0.5 times 0.5, which is equal to 0.25 over 1500. You have to divide that, which becomes 0.00017, and once you square root that, the answer becomes 1.96 times 0.013. Now you have your confidence interval, which is 0.5 plus or minus 0.025, but you still have one more calculation to make. To make this into percentage, you have to plus and minus 0.025 from 0.45 and times it by 100. For A, it is 47.5%, and for B is 42.5%. Therefore, the confidence interval is 42.5% to 47.5%. This means that any given score will fall under the category cars, trucks, and vans as driver for mode of transportation, which is between 42.5 and 47.5%.
Now we will be using SPSS to produce confidence intervals for the sample proportions. SPSS does not provide a program specifically for constructing intervals for the sample proportion. However, we can use SPSS to calculate the sample statistics, namely proportions, on which the interval estimates are based. Once you know these sample statistics, the confidence interval for the sample proportion is easily computed. To illustrate this process, we'll construct a confidence interval for mode of transportation. First, calculate the sample proportion using the frequencies command. From the menu bar, click Analyze, Descriptive Statistics, and Frequencies. Find Mode in the left-hand box and move it to the Variable box. Click OK. The outlet for mode of transportation will look like this. Once the table is generated, you can plug the numbers into the formula previously shown.
So how does this relate back to our original research question? Because we set our confidence interval at 95% and our alpha at 0.05, we can assume that 95% of the time a random sample of the same size, 1,500, is predicted to provide the same result of 42.5 to 47.5%. This information has provided a snapshot of the transportation habits of Canadians in 2009, which can be useful for measuring against in the future. Since the census stopped in 2011, data from 2009 can still be used to some extent to predict future transportation use, shaping policy proposals and budget allocations. Before we end this video, we would like to bring to your attention a minor numerical typo in the Healey and Prus textbook at the bottom of page 179. In the example provided, the textbook shows the numerator as 0.5 multiplied by 0.05. The numerator should be 0.5 multiplied by 0.5, because 1 minus 0.5 equals 0.5, which is 50%, not 0.05, which is 5%. The remainder of the example is correct. If you are interested in further readings on confidence intervals and inferential statistics, which obviously you are, please take a look at Chapter 6 in the Healey and Prus textbook. We have provided two other sources for further reading. The first source looks at common errors in quantitative methods for the social sciences, while the second source explores the mathematical explanation for using alpha at 0.05 or 5%, as well as a detailed explanation of confidence intervals and inferential statistics.